Okay, everyone, so it's time for another CSES problem, and this time we are solving Apple division. And actually, I already solved this problem. You can see here two incorrect submissions and then a right one. So, if I already solved this, what are we doing here? So, actually, I saw a solution for this problem which I've never seen that approach before, so that's why I wanted to implement it myself. So basically, the current solution looks like this. So it's actually, let's read the problem statement first. There are n apples with known weights. Your task is to divide the apple into two groups so that the difference between the weights of the groups is minimal. So basically, we are given a list of weights and we have to divide it among into two groups so that the difference between the groups is minimal. You can see they've given a sample test case over here. Group 1 has weights 2, 3, 4, so total 9, and the other group has weights 1 and 7, so totaling 8, and 9 minus 8 is 1. So that's the output. So my current solution uses recursion to generate all of the subsets, and basically we keep track of them using sum because we don't actually need the values, we only need their sum. And once we have placed all of the elements into two groups, we calculate their difference and return its absolute value and keep track of the minimum. So basically this is like basic recursion here, basic recursion to generate all of the subsets. So what I want to do right now is to write an iterative solution for this problem. So let's discuss how the iterative solution works. Okay, so basically for wait a second. Okay, so we have n elements, and for n number of elements, we have to divide into two groups. So there can be 2 to the power n subsets, right? So what we are gonna do is we'll iterate from 0 to 2 to the power n minus 1. Okay, and basically let's take an example. Let's say n is 3. We have 3 elements. So then 3, 5, and let's say 4. Okay. So for 3, 5, and 4, n is 3, the number of elements. So we will be going from 0 to 7. Now let me write the binary for this. Okay, so 0, 0, 0, 0, 6, 7, 8. Hmm. Then 0, 1, 0. It's really hard to type like this. And then 0, 0, 0, 0, 1. Okay, you see that? Perfect straight line. Okay, so as you can see in the binary of these numbers, like we are kind of generating all of the numbers, three-digit numbers we can generate with 0 and 1. Okay, so basically we have two types of numbers we can use, 0 and 1, and when we write, when we are like writing all these elements, we are generating all of the possible values we can create with 0 and 1. So what we are gonna do, we are gonna use this property, or you can say logic, to divide the elements into the two subsets. So basically, if the value we are iterating from 0 to 7, let's say the current element is 2. Current number, sorry, not element. So and our set has three elements. So we will go through its binary. It's not this one, it's this one, right? 0, 1, 0. Okay. So the our array look like this: 3, 3, 5, and 4, right? So first value is 0, and we have like two groups, right? So this is our group 1, this is our group 2, 1 and 2. So the first element is 0, sorry, the first bit in 2's binary representation, the first bit is 0. So, and our first element is 3, right? You can see here. So 3 will go here. And what's next? The next one is 1, and at 1 we have 5. So 5 will go here. And the next one was 4, and we have 0 over here. So 4 will go over here. So you can see we have generated one of the possible subsets combination. Similarly, in this case, for 0, all of the elements would have been in the first group. Okay. Yeah, I think you should get the idea by now. So this is it. So we are going to use this property to, or rather use this idea to generate all of the subset combinations, and then basically keep track of the minimum difference and then return that value. So yes, this is also a brute force approach, but it's just that we won't be using the extra stack space that we were using during the recursion, right? Because in recursion we are using, in worst case, I think an O of n stack space was being used, since all the, yes, the O of n case, because if you look, okay, so basically our tree would look like this. Let's say, if you look at the code, mm, so for the first, like, for the first time, every element will go in group 1. For the first combination, in group 2 will be empty. So it will look like this. The recursion tree goes here. This is currently pending. This side will execute. So we will pick again here. It goes in group 1. It goes in group 1, so on. So its height, you can see it will be n. So that's why we're using O of n stack space there. But in when you use a loop using this solution, we won't be using that. So that's why this solution is better than the recursion based solution. So let's code this up then. Iteration iterative.cpp. By the way, when I saw this question for the first time, I thought like we will solve this using sorting or something, like sort the elements and then keep adding one element in the group, and then whichever group has lesser sum currently, we will add element to that group, right? But actually, no, not right. So yeah, actually, normally I would have like tried the brute force approach first, which I wrote here, not sorting one. But it's just that I solved so many problems from the sorting topic, not so many, but some problem from the sorting topic. So, like in my head, there was sorting going around, like sort, sort, sort. So, which is why I'm thinking I should like write a little script and which will like give me a random problem from the CSES problem set to solve, like which I haven't done before. After solving this question, I will be working on that. Okay, so for now we have to iterate. Let's call this B. We have to iterate from 0 to 2 to the power. And next one. So while B is less than this value, we will do B plus plus and then in I equals 0, I less than n, I plus plus. And now, how do we like iterate over the bits of an element? So basically, like how do we know this is 0, this is 1, this is 0? So it's really simple. First, let me take this long define. Okay, LL sum 1 equal to 0, sum 2 equal to 0. Okay, and then if e ampersand and so if this is true, then the current bit is 1. Okay. So if the current bit is 1, this part will execute. So let's just add it to bucket 1. I mean sum 1. And so else we will add just to sum 2. And then after we are done with this, keep track of the minimum difference. Okay, I'll just create this variable above after writing this part. So minus 1 to amps of sum 1 minus sum 2. And then and if function to call main. Okay, I guess the result of these two will be long and this is an integer, so that's why it's giving an error. I think if I convert this to long, long, the error will go away. Hmm. Yeah, if hmm, the output for this test case should be 2. I think below this appropriate array. Okay, so this is not what it should be. Let me check the test cases faster. Let's try it with this one. If something's not right, yes. Okay, I get it. I've made an error over here. This should be I. Still doesn't seem okay. Test case. Okay, it should definitely not be 0. Setting left to 19 here. The different test case. And 0. Okay. To tell that's I'll logging out these two values. Okay, so these two values are very huge, and this is not how it should be. Actually, how many times are we? Okay, I get it. After each of these, this should be declared over here. We don't need to declare them outside. No, it should work. Yes, 2. That's the correct answer for this test case. And for this one, it should be 1. Okay, not 1. I change the test case. Yes, this should be the answer for the test case. Like, I can show you the test case. So it's taking in this one. So basically this number goes in one bucket and the rest all of these in another bucket. So sum will be 14. So 14 minus this huge number should end with 50, and it's ending with 50. Working as expected. Let's submit this. I must say I'm really impressed with the iterative approach. This was the first time I've seen something like that. Accepted. Okay, so I guess that's it, guys. Bye.